Okay, so so I want to look at the second derivative test, and I know that there's a warm up here, W for the win. But I want to start with the second derivative test because this is going to be a warm up. So hopefully depending on the sequence of when you're watching this video, you either solve this and it makes sense, or you know that you have to still do that. But I want to start down here with the actual definition of the second derivative, or what does it show? So it says, let f of x be a continuous function on this closed interval. And it says twice differentiable, just meaning that you can take two derivatives without anything happening. In most all polynomials, like think about that, like taking two derivatives is no big deal. So you're just kind of defining that it's a function that's kind of like that, where you could do two derivatives. Okay, so if your second derivative, if it is positive, then your function f of x is concave up. And we talked about this on Friday's video, that the second derivative is going to give the curvature of this particular function. So something that is concave up, would be a function. Let's say you've got this piece here. The concave up part would be the part that looks like, it's open like a cup, right? Like this part right here. So this part right here is considered concave up. So that is always going to be true of a positive second derivative. That curvature is concave up, or the concavity is positive. Now, if your second derivative is negative, then f of x is concave down. And again, thinking about this graph that I just showed, the concave down piece would be, thinking like down like that, like opening down. I always think like down like a frown. Okay. Now there's a transition point, right? At some instant, you have to go from concave up to concave down. And where that changes signs is a critical value, or I should say a value that we're interested in. Right there, that point right there is called the point of inflection, and I'll define that down below. Point of inflection. So the idea is, and you can abbreviate it POI. So the idea is that the curvature changes at that instant. So if your second derivative is 0 and changes signs. Now, I should probably also say, or if your second derivative does not exist, although it kind of goes against that, goes like that twice differentiable piece. So there's kind of an exception to the rule here. And you change signs, then C is a point of inflection. Now, the undefined one that I'm thinking of is our cube root function, right? So thinking about that function, like y equals, or any odd index, really. If you look at that, so this function here, actually I'm augmenting it, right? But at that instant, there's a vertical tangent line. So it's the second derivative and the first derivative is undefined. But notice the curvature change, concave up to concave down. So there's an example of a point of inflection. Okay? And then another one, if you just had any other, again, polynomial function, I kind of like that purple color, by the way. Any other polynomial function, you don't have to have a horizontal tangent line. I mean, you could, but any other polynomial function, like if this almost looks like a fourth degree power, look for the curvature changes. So like maybe there, like you're going from concave down to shifting concave up. So there's going to be a point of inflection there. And then maybe somewhere here, you're switching again from concave up to concave down. So that's another example of a point of inflection. And you could, like I said, you could always abbreviate POI. Very, very common. So now we had a little bit of a foreshadow of this last week, because saddle points, if you remember, saddle points emerge from the first derivative test. Oh my goodness. Try this one more time. There we go. And so we've seen, so saddle points emerge from the first derivative test, even though they are a second derivative feature, because those saddle points are also points of inflection. So remember, if x equals a saddle point, then the first and second derivative is 0. First derivative is 0. And I should probably say first derivative at c. F prime of c equals 0. f double prime of c equals 0. And then I should also have added and change signs, right? Because being 0 is not good enough. Remember, that's our worst motivational speech ever. And change signs. If x is equals to the saddle point, then the first and the second derivative is 0. All saddle points are points of inflection, right? But not all points of inflection are saddle points, because that first derivative doesn't have to be 0 for it to be just a plain old point of inflection. Okay, so some terminology, some definitions, and some images of what are we looking for the second derivative. We're looking for curvature changes. So again, a cubic function here. It says, let's look at the concave up, concave down. Are they saddle points? How would you analyze that? So we need the second derivative. Anytime you see concavity, you should be thinking second derivative points of inflection. You should also be thinking second derivative. So let's do it. So first derivative is equal to 3x squared minus 3x. And then the second derivative would be 6x minus 3. And so thinking about that second derivative, we'd want to know, well, where are the zeros? Because we have to change signs, and that would happen, if you have a 0, and as long as you change signs, you're good. So set equal to 0. 6x minus 3. Oh, so x equals 1/2. So potentially that's a point of inflection. So then we can take a look at what does that second derivative look like on a number line, on a sign graph. So pick 1/2 as our boundary. And if you take this second derivative and pick things that are bigger than 1/2, say 1, you know that things are going to be positive. So, and then things that are less than 1/2, like let's say 0, is going to be negative. So you're shifting from something that's concave down, because remember it's a second derivative test, to concave up. So you did switch signs. So that means that 1/2 is definitely a point of inflection. How do I know it's a point of inflection? Because f double prime changed signs at that instant. So intervals where it's concave up, let's go ahead and answer that. So concave up, that would be 1/2 to positive infinity if I write that as an interval. Concave down would be negative infinity to 1/2. Are there any points of inflection? Yes. Now, is this a saddle point? Well, we can answer that if we know what its first derivative is. So if the first derivative is also 0, it's a saddle point. And we had the first derivative here, so we could say, well, when was that equal to 0? Well, 0 equals 3x squared minus 3x. And we can factor out a 3x, we get x minus 1. And so when does that equal 0? Oh, when x is 0 or when x is 1. So if I'm analyzing my first derivative, like simultaneously, which is actually a really smart thing to do, here's 0 and here's 1, and not like 1/2 is not one of those values. So it's interesting that the 1/2 is right in between those 2 points. And if you think about what does the first derivative test measure, it measures whether your function's increasing or decreasing. And so if you were to pick something bigger than 1 and put it into this first derivative, you would get a positive value. But a positive value for the first derivative means that you're increasing, right? You're going up, which sort of is like part of like this half of that branch, right? And then all of these were odd multiplicity, so then this would be decreasing. So you're going down, and then this is increasing, and so you're going up. So even without this concavity test, you can almost see what the concavity has to be, right? Just by the nature of how you're changing from increasing to decreasing, like increasing to decreasing to increasing. So at some moment in time, look at that, there had to have been a point of inflection. So again, this second derivative test, again, just helps us get a picture of what's happening with this particular function. Okay, and let's do, again, one more in this video. Again, just thinking about how do I use the first and second derivative test to kind of analyze this. And so drawing those sign charts is actually a really, really smart thing to do. So let's go to maybe this color here. It's kind of brown-green. Let's look at our first derivative, which would be half of 4 is 2. So 2x cubed minus 24x, and the 3 goes away. And then like the second derivative, I'll do over here, would be 6x squared minus 24. So again, like both of these functions are polynomial, so there are no undefined moments, but we should solve to see when the zeros are. So setting this equal to 0 and factor by grouping, that gives me x squared minus 12, right? 2x cubed minus 24x. And then this is a difference of squares. Even though root 12 is not a perfect square, you can still factor it. X minus root 12 and x plus root 12. And so, the zeros here would be 0, root 12, and negative root 12. Setting this equal to 0 and factoring out a 6, we get x squared minus 4. And that is a difference of squares, and that is a perfect square. So x minus 2 and x plus 2. So the zeros of the second derivative are plus or minus 2. So let's simultaneously analyze our first and second derivatives. So again, thinking about them as a number line, or on a number line, a sign chart, if you will. And here's our second derivative. And put in the critical values and kind of draw it to scale. So 0 would be our first derivative, and root 12, which is bigger than 3, because root 9 would have been 3. So root 12 and negative root 12. But then 2 and negative 2 would have fit somewhere here. So there's 2, and then there's negative 2. So I'm trying to think about this as if it's drawn to scale. And I want to make that negative 2 even just a little bit closer there, just so I can see. Okay, so let's do that first derivative first. Let's think about putting in values, and bigger than root 12, so you could put in 4. If you put that into each of these factors, or thinking about that, 4 squared is 16, that's going to be positive. And I really love using multiplicity. Each of these are odd factors, right? Degree 1, degree 1, degree 1, which means that since these multiplicities are all odd, they have to change signs. So go from positive, this must be negative, this flips to positive, and this flips to negative. So we are decreasing, we are increasing, we are decreasing, and we are increasing. Now I can already start to see that curvature, and I'm anticipating some changes of concavity. So I'm anticipating some points of inflection. So now we go to the second derivative, and on the second derivative, so we're plugging into here. So numbers that are bigger than 2, let's say 3, that keeps things positive. And then again, since these are odd multiplicities, that means this would be negative and this would be positive. You have to switch signs. So we're going from concave up to concave down to concave up. Now these two sign charts really tell a lot, but that's not good enough on the AP exam. You have to do more than just show a sign chart. So, then you'd have to just analyze and say, it's increasing on this interval because the first derivative is positive. It's decreasing in this interval because the first derivative is negative. So, but this is a great visual to kind of see what's happening as I start analyzing this particular function. And so, if I want to say increasing, okay, it's increasing from negative root 12 to 0, union root 12 to infinity, and then it's decreasing from negative infinity to negative root 12, union, there it is, 0 to root 12. I feel like every time I get to the corner of my tablet, my neatness definitely is lacking, I guess. Yeah, I get messier. Okay, and then concavity, when is it concave up? So concave up, negative infinity to negative 2. Try to go slower. Negative 2. Union 2 to infinity. And then concave down from negative 2 to 2. Now, key points of inflection. Yes, this is a point of inflection, and this is a point of inflection. So I'll make it a point, pun intended. I'll make it a point to say, okay, well, x equals plus or minus 2. Those are points of inflection. right? And how do I know that those are points of inflection? F double prime of x changes signs. Okay, a little more. Oh, too much. F double prime of x changes signs. Way too much. There it is. Changes signs at c equals 2, c equals -2, or x equals 2, x equals -2. Those are points of inflections because the second derivative changes signs. And as long as you talk about the fact that it's changing at that instant, that's exactly what you need. Again, our worst motivational speech ever, being 0 is not good enough. But that means just don't be 0. Make sure you're also changing signs. And we should also know that this right here would be a local minimum because our first derivative changed from negative to positive. This one right here, our value would be a local maximum because our first derivative changed from positive to negative. And then here, our first derivative changed from negative to positive, making that a minimum. And I almost caught myself using the word it. But remember, we want to avoid those indefinite pronouns. We want to be very specific, especially now since we have the first and second derivative test. So we've got to clearly indicate which of the functions we're analyzing. Okay, a little bit longer video, but a lot of good information. And then the next video, we're going to analyze the same thing, but use a graph to help analyze. And so that, again, such a common question on the AP exam.